All right, so again, we defined that the 0 is x equals 0, the asymptote at negative half. You could do the horizontal here and say it's 1. There is a horizontal asymptote y equals 1. I typically do polynomial division very quickly, 2x into 2x plus 1. You guys are thinking, why bother? But if I do this, I can rewrite the function like that. And when I rewrite this function, you guys, this is just what I enjoy doing because this is 10 times faster in the long run. That I can rewrite the red function as this blue. And I said there's a horizontal at 1, so you can see that right here, right? Because this is a reciprocal function. We said that negative half was the asymptote. Does everybody agree that the green curve represents 1 over x? Right? That's our parent function, 1 over x. I have negative, and I have the curve shifted over a half, and I have it flipped. So when I do this, and I get rid of the green curve, I get this. There's a sketch of the graph really quickly, and it comes from polynomial division. And I think the domain and range, you knew the domain and range from your asymptote, so the domain is all reals, x not equal to a half, negative half.
Yep.
Y is an element, all reals, y doesn't equal 1. Listen, you really, the sketching of the graph, it depends on where you're going in your life. If you're going to an engineering degree, this helps you quite a bit. You're going to go to STEMs. When I was in mechanical engineering, the ability to make these graphs will make your life easier. If you're becoming, I don't know, a non-STEM in calculus, this is your last math class for college credit, probably, all right, Sam, you probably can get away using your calculator on this, okay? But again, does everybody see why the horizontal asymptote is 1 up here? 2x over 2x, right? The highest powers. And that's defining this line in the range, okay, guys? And again, identifying these functions as parent functions so you can see what to do. I like dividing and having it pop out. And I will always do it that way in class. I'm going to do this problem. It says show that f of x is continuous on 1 to negative 1. Now, remember where we left yesterday. We've defined removables, jumps, and infinite discontinuities. Everybody with me on those?
Yeah.
So I look at this function, f of x equals 1 minus the square root of 1 minus x squared. Does everybody agree I can flip the order? Negative radical 1 minus x squared plus 1. What I want you to realize at this point, I suppose I should have a negative sign, that if I think of this, I just take that part of it right here. Maybe you guys don't remember this, but this is a semicircle, the red portion that's under red. And when I square it out, it's because I can get to this, x squared plus y squared equals 1. The negative portion is the lower part of the circle. So what I did here in red is I sketched the lower portion of the circle underneath the axis, right, with a radius of 1 from my general form, because that was the negative portion up here. And then what does the plus 1 do? Shifts the whole smiley face. The red smiley face goes up 1 to the purple smiley face, right? So we have a function here, and I've made the graph. And I suppose, again, we can put this on our calculator and get the same answer, all right? We are going to define that this function is continuous from 1 to negative 1. So the question is how can you prove that? When we learned our limit laws the other day, remember? You wrote down all these rules. Well, I moved it up 1. This was plus 1. Okay. Okay. Oh, all right. So, right. I just handled the radical. I just handled the radical to prove this, and then I shifted the 1. Okay. Anyway, back to this. We can show through limit laws that this function is continuous. Does everybody agree when you look at the purple curve, it's continuous? And how do you know? You know it's continuous because the limit as x approaches a of f of x equals f of a when x is between where? -1 to 1. You can see it on the purple curve, right, guys? Anywhere the limit exists, thus it's continuous because it's equal to the value of the function. This is the big deal about continuity. We could plump. Now, if you're at a college campus, they would absolutely do this proof, and he'd probably spend 15 minutes on it. He's going to take the limit as x approaches a of f of x, the upper function here. And he's going to say, well, that's equal to the limit as x approaches a of what the function is, right? All right. What do we know from our limit laws? I can insert this limit to both portions. Do we agree? Right? Well, the limit as x approaches a of 1 is simply 1, right? Now we also know from our limit laws that we can put the radical over the top of the limit. This is one of the limit laws you took the other day also. Now, not to bore you, could I insert the limit to both of these portions here? Sure. But let's skip that part because we recognize 1 minus x squared is a parabola. So we'll just insert a. And what do I get? I get that. And what is that equivalent to? Isn't that just equivalent to f of a? If you look at the original function here at the top, have a. A is a variable between, a is between 1 and -1. Right? You're talking this step right here, Morgan? Up, this step, this step. All right. What about it? The limit as x approaches 1. The limit as x approaches a of 1 is always 1. So this is, yeah, it's of a constant, it's always 1. Okay. But everybody, here's what I want you to show. Think about this. The whole way down, it's been limit as x approaches a of f of x. This is our bread and butter statement for continuity from now on. If we can show that as the limit as x approaches a of a function is equal to the value of the function, we know at that point it is continuous, period. All right? And this is section 2.5, and this is what continuity is. All right? When it is not equal, when the limit and the function are not equal, you either have an infinite, a jump, or a removable. Now, we should be able to define them, because you think about it. When you have an infinite discontinuity, the function has no value, right, guys? When you have a removable, you have a limit, but the value of the function is not the same. All right? And when you have a jump, the value of the function equals usually one hand of the function, right? The left or the right, but not the other. So we should be able to kind of see that in our heads. So to bring that back, for a removable, there's a limit, but f of a is not the same, right? For a jump, there is no limit. The left hand will have a limit L. The right hand will have a limit L1, where f of a is equal to one of the two hands, but not both. And finally, on an infinite discontinuity, it could be neither two. I mean, if you don't fill it in, good point. But that would be kind of like removal. It could be neither two. You're right. It could be like this. You mean? But that's both then. That's removable and a jump. Possible. Yeah, it's possible to have no value in a jump. So those are our three discontinuities, and when a limit is equal, we know what we have. All right. Enough talk. Let's do some problems. So again, let's do some limits, get them back form. Plus 1. No, minus 1. Gotta make them the same. All right, try this limit, everybody. Try that limit. Oh.
Yeah.
All right, so let's go back and tell Morgan this. Listen, you just plug it in, right? And it's negative 111. That's the first thing you do with limits. Check fits in. But let's be clear that this is continuous because of this statement right here. It is a continuous function at negative 2. In fact, what kind of function is f of x? What kind of function is this? A rational function. All right? All right, that's right. You'll get better. It's a rational function.
So are we. We've never done this.
Listen, it's a rational function. Here's what where is this function undefined? Where is this rational function undefined? One spot in all of x, right? What is it? 5/3. Whoever whispered that, nice job. Was that John? Hey, John, you're absolutely right. Guys, x is an element of reals. X cannot be equal to 5/3. You guys agree? That's John's right on. That's the domain. Guys, where's the only place that we can't just plug in the value of the limit then? 5/3. Everywhere else, because a rational function is continuous everywhere else, we can just get the value. Well, all of a sudden, when you have a rational function, there's usually only one or two spots to worry about. You guys agree? What kind of functions are continuous everywhere? Parabola, which, guys, how about power functions? Parabola, x cubed, x to the 4th, x to the 5th. Oh, you're picking on my drawings now? Go away. All right, how about any power function, guys? X to the n. Those are continuous everywhere. Do you guys agree? The domain is all reals. We don't have to worry about limits with power functions or exponentials or no, because they're called logs. They're logs, and we don't deal with them for a while yet. I saved it at the end. But power functions, polynomials, lines, guys, these are all continuous functions, right? All right, polynomials. Guys, when you have a limit of a polynomial, you just plug in and get the value. The limit of a line, you just plug in and get the value. One more that's usually forgotten. How about sine and cosine? Guys, sine and cosine are both continuous, right? Everywhere. So again, we have these types of functions, and this is why I make a big deal about knowing their names so we can talk about them. But rationals, there's one other type that we haven't talked about that's continuous in its domain. Just its domain. Anywhere there's a domain. How about root functions, guys? In their domain, they're continuous everywhere, right? Once you define the domain, the square root of x, if you want to take the limit of x approaches a of the square root of x, it's simply the square root of a, as long as you're in the domain. Again, continuous functions, the limit and the value of the function are the same. You probably think, I'm beating this to death. Right, it doesn't go negative, but a is defined. It has to be inside its domain. It has to be inside its domain. You can't take the limit as x approaches negative 4 for a root function. That's not in its domain. All right. All right. And that gives us power to do things like question is this function continuous? Yes or no? And we're going to work through why. All right. Guys, you agree that's algebraic? It's an algebraic function. It's got a power inside a trig. It's something completely different. So again, I want you to think of composite functions, right? When I look at this, maybe I'll call this capital F, so that we can make a statement like this. Capital F of x is equal to f of g of x. You guys agree? And you guys agree, in this case, f of x is equal to sine x, g of x is equal to x squared. So, is x squared continuous? Yes. What is it? It's reals. Boom. Done. Its range is 0 to infinity. Does 0 to infinity work as a domain of sine? Yeah. It's always going to work. So this function is continuous. All right. We can work through the composites. All right, and work our way through. They don't have to be pretty either. They can be ugly. They can be ugly functions. We could try functions like this. Not what I wanted. There we go. There. Again, when I look at this function, it's not rational, right? It looks like a rational. It's a combination of a rational and a root, so it's an algebraic function. It is built out of piece parts, okay? So the question is, what about this one? Is this going to be continuous? Now this one's a lot harder, I think. I see 3 functions, guys. You want to try it? I'll give you a second. I'll pause. Yep. You can do it in 2, maybe 2. I'm going to do it in 3. I'm going to do it f of g of h. I'm doing the -4 separately. All right. Give it a shot. I'm going to pause for a moment. I forgot. So you can set up all these piecewise functions. Well, yeah, Morgan's saying, what? Morgan, I just skipped about 6 minutes of talking. You can set all these up and go through those. Guys, is it just as easy to look at the bottom here and say, can that equal 0? Someone had to have thought of that, right? Like, Mr. Anderson's lost his mind. He's doing all this work. Couldn't we just say, couldn't we start with this statement and go from there? The answer is yeah. All right. No, it's not equal to 0. And square both sides, and you get 3, guys. You get that 3 is not continuous here, okay? Now, what about everywhere else? The answer is everywhere else is continuous, guys. All right? You're going to find that out, all right? Yeah, right here to solve this. You solve, oops. If you solve this, you're going to get down to 3, okay? And -3, plus or minus 3, as a place that this doesn't have.
Oh, I got it.
Okay. All right. So you're thinking, who cares if functions are continuous? Is anybody thinking that? Yeah, Ryan is. Guys, and I hope you guys are too. Who cares? We spent a whole bunch of time, we spent 2 days trying to make sure we understand where it's continuous and not continuous. And it comes down to 1 theorem. I'm driving my car, okay? It's probably noteworthy eventually. And I'm going at time. All right? And my odometer reads something at time A. If I start driving from Juda, go home to Broadhead, and my mileage says 100,000 miles dead on my van, and I get home and it says 100,010 miles. It takes 10 miles for me to get home. Everybody with me? Did I have to go through 100,005? Why? Why? You're right. I had to, right? Why? So why? Why couldn't it just go from 100,000 to 100,010?
Oh, it's the intermediate value.
Because, guys, we don't do this, do we? When we drive our car. We can't take a jump. Does everybody agree? Because what do we know about the odometer on my van? It's continuous. In fact, if I drive, depends how I drive. I drive slow in Juda, then I drive really fast, and I drive slow in Broadhead. Right? I mean, my graph going home looks something like this. It takes me longer to drive through Broadhead almost to get to my house than it does to go between Juda and Broadhead. All right? It proves that in between.
This is you can't stop.
Nope, this is proving that there's a value in between two values.
Oh.
Okay, it's called intermediate value theorem. Did you guys do it in pre-calc last year?
What?
Did you do it? Intermediate value theorem, IVT. Nope. Okay, don't worry, we're starting from scratch. Doesn't matter.
Go ahead.
It's called intermediate value theorem. All right. Yeah, we did a little bit, like I did.
We never really called it this.
Yeah.
Did you guys do it? Did you guys do that homework over the summer?
No. Not this year. Not this summer, because I knew you guys were coming.
Cool.
All right.
Drop off.
Everybody, you guys agree if there's some C value in between A and B, that there is some N value, and if the function is continuous, ooh, that's awful little. All right, that if there's some C value between A and B, and N is between f of A and f of B, that the function is continuous, it has to pass through N at least once. Think about this. If I go back to A and B, and I say there's a C between, and here's f of A, and I'll have it be an increasing function just to keep it easy. And I say, oh, there's point A, f of A, and here's point B, f of B. Is there any way for a continuous function to go from the black dot to the blue dot without passing through N? No. Now, I can try, but eventually if it's going to be continuous, somewhere that C value is going to hit, right? I might have to move C over here, all right? Or I could do this, right? And then it's right there. Okay, there's C and N. All right. Okay. Now, does it have to hit N? Can it hit N 3 times? Sure. I can hit N once, twice, 1, 2, 3. There we go. Once, twice, 3 times. There's C1, C2, C3. All right. This is a big deal for us in calculus because often, guys, we can't prove N exists right away. But what we can prove often is that A exists and that B exists. And we want to know if N is around. And if we can prove A and B exist, and we can prove that the function is continuous, we know at least one value of N exists, right? There might be more, but we can guarantee one. All right? It's called the intermediate value theorem, okay? And if I put up the definition, this is what it is. The definition is this. Intermediate value theorem. All right, this is probably noteworthy. And again, it's the same picture, but I want to go from scratch because I am a sloppy writer. Yeah.
Are you recording this?
I am. Thank you for asking.
Yeah, just in case.
All right. It comes down to this blanket statement, guys. And I always want to say it the right way, so I always do it on my notes. F is continuous. That is the big deal, guys. You have to have that. You have to be able to prove that. That's why we like knowing that rationals, polynomials, trig, lines, power functions, they're all continuous. Because then I can say stuff like it's a polynomial, therefore it's continuous. Right? For these proofs. Okay? Or these prove it so we can do things. Now, if suppose F is continuous, on the interval A to B, right? Between A and B. I don't know what's doing outside there, don't care, okay? But in this interval, it's continuous. And we're going to let n be a number between A of F, between F of A and F of B, right? On the graph, you can see this, right? We're going to have n between F of A and F of B. Where, we better make sure of one thing. What do we know about F of A and F of B? They're not equal. Do you guys agree? These are different values, right? Because I'll show you in a second why F of A and F of B can't be equal. Okay? Then there exists, then a number exists C, right, which I have on the graph, in the open interval A to B, okay, such that what? Such that F of C equals N. And this is a big deal for us in calculus. We'll use this all the time on our AP problems. All right? It's kind of like anytime we're emptying tanks or something like that. Almost all sensors in the world work on this principle. Like in corn syrup. My experience, guys, is with corn syrup. We used to have to buy thousands of gallons of corn syrup to make Spam. Yep, it was great. I love working Spam. Point is, guys, the sensor would read some n value between A and B. It wasn't indicating some magical level. It was just saying, hey, you've passed the lower limit. Call the semi and have 1,000 gallons, 10,000 gallons of corn syrup delivered. All right. This is every day used out in the world. We will put this into principle into practice on Monday. We'll try to catch Morgan up. I'm going to stop recording. Does anybody got any other